Right, so let's figure out what the law of averages actually says. We spent quite some time saying what it doesn't say. And so here's the statement that we made before. Informally, as you keep tossing, in the long run you get about half heads. We noted that this is to do with proportions, not the number of heads. And it's about the proportion of heads being not exactly a half. That's not likely with a large number of tosses, but close to a half. So what do I mean by close? Well, I can define it in any way I want. For the law of averages we discussed, it's important to think of it as half, 50%, plus or minus a certain error in the percentage. So 50% plus or minus, for now I'll take 5%. 50% plus or minus 5% in terms of proportions, that is 0.5 plus or minus 0.05. 45% to 55% heads. That's what I'm going to look at for now. So what are the chances of getting between 45% and 55% heads? When you got your probability calculator, we can do this. In 100 tosses, you're looking for the chance of getting heads in the range 50 plus or minus 5, that's 45 through 55. That chance, your calculator will tell you, is about 73%. With 1,000 tosses, 50% plus or minus 5% is 500 heads plus or minus 50 heads. That's 450 heads to 550 heads, and that chance is almost 1. 0.998, very, very high, and this is the law of averages. A percent of heads in the range half plus or minus a fixed amount. Increase the number of tosses. The chance goes up and up and up, and it's going to go to 1. And that is now beginning to formalize the law of averages. So as you keep tossing, in the long run, the chance that the proportion of heads is in the range, the probability of heads plus or minus a fixed amount, so a fixed error in the proportion, that proportion goes to 1. And you can take this fixed error to be as small as you want. We took it to be 5%, but we could take it to be any other number as long as we keep it fixed as the number of tosses go up. So why don't we do another example where I take 1% as my error. That's a tiny error, a very small amount of error I'm allowing. So 50% plus or minus 1%, 0.5 plus or minus 0.01, 0.49 to 0.51, 49% to 51% heads. That's what I'm allowing myself, very, very close to 50. So how does this compare if we look at 100 tosses versus 1,000 tosses? Well, with 100 tosses, 49% to 51% is exactly 3 values, 49, 50, and 51. And the total chance of these 3 values, your calculator will tell you, is somewhat under a quarter. With 1,000 tosses, you're looking at 490 to 510, and that chance is about a half. And by the time you get to 10,000, and your probability calculator in the online text won't do it, but there are other computers that will. That's 4,900 heads to 5,100 heads, and that chance is more than 95%. And you can imagine if you have 1,000,000 tosses there, that chance is going to be even higher still. And so the chance of getting heads in the range 50% plus or minus a fixed error is still going to 1, even though the error that we're allowing ourselves is now smaller than what we had allowed ourselves before. We had allowed ourselves 5% before. That is what the numbers tell us, just plugging into the binomial formula. And as we did last time, we're going to say, all right, this is by formula. We accept with bowed head what the formula says. It would be very nice to have a visual sense of what is going on. And so what we're going to do is we're going to use the binomial histogram program in your textbook and see what's happening to the picture. Here's the binomial probability program in your online text. Parameters n and p, and by default they're starting with n equals 5. And what we're going to do is we're going to look at n equals 10 because we've seen that before. Right, so the number of heads can go from 0 through 10. The central bar is at 5. And there's your lovely bell shape. Yes, those of you who have taken 2.1x are seeing the bell shape emerge. And that's all fine. That's exactly how we expect this histogram to look. And now we're going to increase the number of tosses, and I want you to watch what's happening to this horizontal axis. N equals 20. You'll notice that physically on the screen, 0 through the number of tosses occupies the same space as it did before. I'm going to go back. 0 through 10 in this case occupies essentially the same space as 0 through 20 in this case. And now, of course, it's not true that there are the same number of numbers in 0 through 20 as there are in 0 through 10, but what's being kept constant is the proportion. 0% to 100% is occupying the same physical space. And what you saw was that in that case, if you keep proportions comparable from one histogram to the next, then with 10 heads, your histograms kind of spread out about 50%, as you would expect. With 20 tosses, it's slightly more squished in. 0%, 100%, and not a lot of action in these very low or very high percents. And what if we up that to 40 tosses? What do you think is going to happen? It's going to squish in some more. There you go. And the proportion of heads is getting closer and closer and closer to 50%. The chance that you are away from 50% is getting small. There's more and more of the proportion scale is showing very little probability. 40, oh, how about 60? Yep, still further squished in, moving right along. How about 100? And so what's happening to this histogram, if you think in terms of proportions, the histogram is turning not only into this lovely bell shape, but into a spike at 50%. So if you take any fixed interval around 50%, eventually, as the number of tosses gets large, almost the entire spike is going to be in that interval. So the chance of that fixed interval, 50% plus or minus a fixed amount, is going to be almost 100%. How far can I go? 200 tosses, and I think I can go to 500 tosses. That's about as big as it'll let me get. Yep. And you can see that spike as you can imagine that if you increase the number of tosses still beyond 500, that spike will get taller and skinnier. And that is a visual description of what the law of averages is doing. The probabilities are bunching themselves around 50%. So we talked a lot about coins. Does it have to be coins? Does it have to be 50%? Well, I mean, we've got a calculator, so why don't we play with our program here? This was the default. It started with 5 tosses of a coin. How about 6 rolls of a die? Should we try that? So we're looking now at the number of sixes. So this is 0.167 is 1/6 roughly. And we're looking at the number of sixes in 6 rolls of a die. When in 6 rolls of a die, how many sixes do you expect? About a sixth of the time, yeah, you think you're going to get a 6, so you expect 1 6 in 6 rolls. Not surprisingly, that is the highest bar. You're quite likely to get no 6s at all, and that's a substantial bar as well. Then there's some chance smaller of getting 2 6s, 3 6s, 4 6s. You're really not expecting 5 or 6 6s in 6 rolls of a die, though of course it is possible. So these probabilities do not look normal, but they're perfectly understandable. And the peak is at 1/6. So what happens if we increase the number of rolls? So if we look at the number of sixes in 60 rolls of a die, then just roughly how many sixes do you expect? 10, yeah. 1/6 of 60. So let's put in 60 here and aha. Once again, the proportion scale is remaining constant, 0% to 100%. This here is a sixth, that is 16.7%. And the probabilities all bunched up near the 16.7%. There's virtually no visible action beyond about 20% at all. And what do you think is going to happen if we increase the number of rolls still further? So 1/6 is going to be just around here, and you're going to have a histogram that's even more of a spike around here. So let's go to 120 rolls, and there's your spike at around 1/6. 20 out of 120 is a sixth. How far can I go? Can I do 240? I can do 240, and you see the spike gets closer and closer and closer. 40 out of 240 is a sixth, and so on. So it doesn't matter that you have dice instead of coins, you still have this lovely bell shape. That's interesting, isn't it? And the bell for the proportions is centered at a sixth, and it gets closer and closer to a sixth as you increase the number of rolls. So back to a small number of rolls, 6 rolls. This is not normal. 60 rolls, very close to normal. I can see a little bit of skewness on this side. 120 rolls, very nice. You can see the normal approximations are going to work well here. For now, what we're looking at is just where the normal curve is centered. And it is centered at 1/6 on the proportion scale. So what we're going to do now is formally state the law of large numbers. It has to do with independent repeated success-failure trials. We saw coins, we've seen dice. You can imagine any other set of successes and failures that you wish, as long as the trials are independent. And the probability of success on a single trial is always the same, P. It's a half for a coin, a sixth for sixes in rolling dice, and so on. The law of large numbers says, as the number of trials increases, the chance that the proportion of successes is in the range, your probability, plus or minus a fixed amount, that goes to 1. So 1/6 plus or minus a fixed amount, the proportion of sixes will tend to be in that range, and it is more and more likely to be in that range as you increase the number of rolls of your die. You just quickly see it in an example that is not to do with either dice or coins. It's genetic theory and plants. So you've got plants of a species, and the theory predicts that each of those plants has a 25% chance of being red flowering, independent of all other plants. And I have a hothouse full of these, lots and lots of them in fact, and I want to compare 2 chances. And I have a huge hothouse. I have a field of these plants, and I've deliberately chosen a number of trials so that you can't rely on your calculator. And I want to compare 2 chances. I want to compare the chance of fewer than 2,400 red flowering out of 10,000 plants compared to fewer than 24,000 red flowering out of 100,000 plants. So if I'm going to compare 2 things, I have to find something that's common. What's common is that I'm looking at 24% or fewer red flowering. As you increase the number of plants, the percent of red flowering plants goes towards what? Yeah, it goes towards 25%. That's the actual probability. So as you keep increasing the number of plants, the percent red flowering is going to go to 25%, which is not fewer than 24%. So you should not increase the number of plants. You should stay with a smaller number. Your answer is A. Let's write that down. In both cases, the event that's been compared is fewer than 24% red flowering. But as you increase the number of trials, your percent of red flowering goes to 25%, which is not fewer than 24%. But you want fewer than 24%, so don't increase the number of trials. Choose the smaller number of trials. The moral of this story is, if you want an event that doesn't contain your actual probability of success, you're better off going with the smaller number of trials, because with the bigger number of trials you're going to get to the probability of success, which is not what you want. Had I said, which is more likely, more than 2,400 red flowering out of 10,000, more than 24,000 red flowering out of 100,000, more than 24% does indeed include 25%. And so you do want to increase the number of trials, because you know that the proportion of red flowering plants is going to get close to 25%, which is in your winning region. And so this is a look no hands comparison of these two probabilities. I was simply asked which is bigger. I wasn't asked to find them. So I didn't find them. I just said, based on the law of large numbers, which one is bigger. Now, over the next week or so, you will have a way to approximate these probabilities using the normal curve. But if you are just comparing, frequently you don't actually need to know what the value is. You just have to have a sense of which probabilities are large.